Hello students, if you remember in last period we have seen we have started a new chapter AC circuits. In that case we have seen in last period when AC applied to resistor what will occur, and that we have find out the result that when AC is applied to resistor, it is seen that EMF and current are in same phase. They will start at same point, they become maximum at same point, and they become again minimum at same point. So we can say they are in same phase. So in case of a resistor connected to AC circuit, there is no effect of AC on a value of resistor in terms of current and EMF. Both are in always phase. Now we have to see, we have seen the phasor diagram of that also. We have drawn the waveform diagram of AC to the resistor also. Now we have to see AC voltage applied to inductor. So this AC applied to inductor, AC voltage basically, AC applied to inductor. So we know that inductor means what is a coil. So we can represent the diagram like this. Suppose this is a coil, this is a spiral thing I am going to draw. It is a coil that is said to be inductor, and to this inductor we have applied this type of signal, and this type of signal means what? It is AC applied, E equal to E0 into sine of omega t, that is AC applied to this inductor represented by L. Now under this condition, just you have to remember one point. Whatever the value here they have given, exactly find the opposite value. EMF is given, so our aim in this case is to find the current and check whether EMF and current are in same phase or they are out of phase, or what is different between them, that we have to find out. So point to be remember in this diagram, if the EMF is given, you have to find out the current. If current is given, you have to find out the EMF in the same fashion. So here this is EMF, AC EMF applied to the inductor, E equal to E0 sine omega t, and we know that whenever this AC EMF is applied, current flow from the inductor and it will induce a EMF in that according to Faraday's law. And if L is the inductor, then you can write here E equal to minus L into di by dt. If di is a current flowing through this, then L is the inductance, and this minus sign comes here by the Faraday's and Lenz's law we know. So E equal to d phi by dt, put the value of phi, it becomes L into di by dt. That already we have learned in last period, in last topic we have learned. So that we have applied here, so we get here this term. Now here, as we know that this EMF applied to this AC circuit, it will pass a current, suppose in this direction, this is a current due to this AC EMF, then exactly opposite direction current get induced inside this, and EMF is exactly opposite to this. So that you can write the simple thing that suppose that EMF induced inside this is E dash, then we can write E merge be equal to minus E dash. According to Lenz's law, the direction merge be opposite. What is E? E is this. So we can write minus of E equal to minus E dash. E is this, minus of minus L di by dt. Remember, we have not kept the value of E dash. E is minus of E dash is minus of E. So that we have made it minus. So minus minus becomes plus. Then we get here, it as if this minus cancel with this, we get L into di by dt, that is equal to E. From this find out the value of that, from this equation just find out the value of di, this di. So what we can write, this di kept as it is, di equal to, just move this L to this side, E by L into dt. E by L into dt. Here dt is the amount of time for which current get passed, L is inductance, E is the EMF, di is the current. Okay, so just we have find it out. Now if we want to find out the total thing, total current flowing to this, then we have to integrate this. So let's integrate this equation. So we can integrate this equation like this, and after integrating, just I will write down the next term to this side. So just integrate this equation and just solve it further to find the value of current. Okay, so just I am going to integrate it. So integration of di is what? It is I, or just I will write a small I. So I is a total current is I, and it is equal to what? Put the value of E here, I will put it here also. E equal to E0 sine omega t. If you see this, put that E0 sine of omega t divided by L into dt. E by L are constant. So E0 and L are constant. Take them outside. So we can write E0 divided by L integration of sine of omega t into dt. Integration of sine omega t is what? Cos omega t. And integration of omega t is what? Omega. So we can write this further equation as sine integration minus cos omega t. So we can write E0 divided by L. Integration of this is what? Minus cos omega t minus cos omega t, that is nothing but integration of sine omega t divided by integration of this omega t divided by omega plus some constant of integration that depends on initial values. That's why this constant come to be 0. Now this we can write in the same way as minus sign we have taken, E0 divided by omega L into cos omega t can be written as sine omega t plus pi by sine pi by 2 plus theta, that is nothing but a cos theta is equal to sine pi by 2 minus theta. So cos theta here written as sine pi by 2 minus theta, so it is pi by 2 minus theta. Sine of pi by 2 minus theta, theta in our case is omega t. So sine pi by 2 minus omega t. These are the formulae you have learned in trigonometry in 10th standard. As this minus sign is here, swap the terms. So we can write E0 divided by omega L sine of pi by 2 is positive. Due to this it becomes negative. The omega t is negative here. Due to this minus sign it becomes positive. So we can write sine omega t minus pi by 2. That is nothing but a current flowing to this. If you put this as a I0, we can write I equal to I0 into sine of omega t minus pi by 2. And this equation gives the current and this equation gives the EMF. Now compare these two equations. Current and EMF, if you compare, it is seen that EMF and current, if you compare, we will see that sine omega t is here, sine omega t minus something is there. So we can say current lag behind the EMF by how much? Minus pi by 2. So current lag behind the EMF by pi by 2 we can say, or another way we can say EMF lead. EMF is ahead of current. EMF leads the current by pi by 2. Both are same. EMF is ahead by pi by 2 or current is behind by pi by 2 of EMF. So that is nothing but what? When the AC is applied to the inductor, it is seen that, we can say it is seen that AC applied to the inductor, EMF and current are not in same phase. Current lag behind the EMF or EMF leads the current by pi by 2 we can say. Now we have to write the same, just a graphical part. We have to draw the graph of this. So I will draw it at the top. So just I will try to draw it here. So graphical representation of the two that we have to do here. So just do it here. Suppose EMF start from 0. So EMF will start from 0. We will show. I will just modify this circuit little bit. So just we have to draw the wave now. So it comes down. So I will just erase little bit the small part. Now such type of thing. This is the EMF start like this. This is the EMF. This is nothing but a EMF E equal to E0 sine of omega t. E equal to E0 sine of omega t. Now we say that according to this and this equation, current lag behind the EMF, lag behind means it comes in negative direction. So here EMF start at 0. So this is 0 where EMF start. This negative y-axis, this is positive y-axis. This is x-axis along which we have taken a omega t. Now in that case, as current lag behind the EMF means what? It is behind the EMF. So if EMF start here, the current will start in negative direction like this. So you can write like this. Little bit, they are not in phase now. So current lag behind the EMF by pi by 2. So I will draw it like this. Such type of thing, and that is nothing but I equal to I0 sine of omega t minus pi by 2. So that will use blue color line represent what? Current. and this maximum value is said to be I0. This maximum value is said to be E0, peak value of EMF and peak value of current. Okay, so these are the waveform, and from this waveform you can say EMF is ahead of current or current is behind the EMF. How much angle? By pi by 2. So this is nothing but a waveform diagram they have shown in your book. So I have drawn accordingly. Apart from this, they have just shown the phasor diagram. They have drawn the phasor diagram. So we'll go according to the book. We're going to draw the phasor diagram also. So phasor diagram already we have seen. It will give the vector which are rotating. So just according to the diagram they have drawn, we are going to draw it here, the phasor diagram. So such type of thing they have drawn, and we know that suppose this is a EMF E, this is a current I, EMF E and current I, then we can represent the value. The here it is the peak value of EMF E0, here it is a peak value of current, it is I0, E0, then it is I0, and they are separated by here. This angle is omega t, and angle between EMF and this current, this angle is 90 degree. 90 degree or pi by 2, we can say that here. Then in that case we can just write the equation from this phasor diagram. If we just draw perpendicular to this, this is what this is what E equal to E0 sine omega t na. So it is what E0 sine of omega t. If we draw the perpendicular from this I, if we draw the perpendicular from this I on the same axis like this, if we draw it like this perpendicular, this is what I equal to I0 sine of omega t minus pi by 2. So this is nothing but a phasor diagram that will represent the I0 and E0 are separated by 90 degrees. Same thing they have shown in your book, figure 13.8. Now here, next part remaining is nothing but what? Just we have derived this equation and we came to this part, that E equal to, just I will write here value of E equal to E0 sine of omega t. We have seen up till now the phasor diagram and the waveform diagram and how the current leg behind the EMF, that also we have seen. Now if we see in this case value of I0 specially, I will write here I0 equal to what? E0 by omega L. So it is E0 divided by omega L. So that is according to our equation. If we see the Ohm's law, according to Ohm's law, V equal to IR. So I equal to V by R. If we compare these two equations, I equal to V by R, E0 equal to I0 equal to E0 by omega L. If we compare these two equations, it is seen from these two equations, this V correspond to E0, I correspond to I0, and this R correspond to omega L. So whatever with the resistance in Ohm's law, same function was done by omega L in case of inductor. So it is said to be inductive reactance. Point to be remember, it is said to be inductive reactance, and that inductive reactance represented by X suffix L, inductive reactance, and that is equal to what? Omega L, or we can write this as equal to E0 by XL. So XL equal to omega L. What is omega? 2 pi F. So we can write this as 2 pi F into L. F is a frequency, L is a inductance, and 2 pi is the constant. Now for AC and DC we have to find out first. For DC circuit or DC direct current, we can say, we know that that is represented like this. It is not changing with time. This is time, it is not changing, it is constant. If it is constant, what is the frequency? Its frequency is 0. Whose frequency? DC frequency is 0. If you put here, what is XL? XL equal 2 pi, 0 into L, everything will be 0. XL equal to 0 for DC. If XL is 0 for DC, what does it mean? Whenever DC pass through the inductor, it will not oppose the DC. It will pass the DC. It will means what? Inductor will pass the DC, because opposition to DC that is inductive reactance is 0, so it never oppose, it will always pass the DC. Same thing we have to do, that is the B part for AC. For AC we have to see, for this AC frequency is not 0, you can write like this, it is time and it is changing with time. So the wave changing like this, changing with time, so it has some frequency. So frequency is not 0, so we can write inductive reactance XL equal to omega L equal to 2 pi FL, 2 pi FL. And it is seen that if the AC of more frequency, the frequency is more, XL get more. Higher frequency signal are opposed by inductor, while lower frequency signals are passed by the inductor. So inductor can pass low frequency AC signal, but it will block or it will oppose high frequency AC signal to pass. That is nothing but a capacitive reactance we have seen. Now here you must know about, just you must understand this concept and you must keep in your mind that here in case of resistor it is resistance, in case of inductor it is a inductive reactance represented by XL is equal to omega L equal to 2 pi FL. As DC has a 0 frequency, so opposition to the DC by inductor is 0, it will not oppose the DC, it will pass the DC. But for AC it has a frequency, if frequency is more, opposition is more, frequency is less, opposition is less, so it will accordingly, according to the frequency, it will block or pass the signal. That's why it is said to be inductive reactance. It is again the opposition, but the opposition depends on a frequency. That is nothing but a inductive reactance. Now just we have seen AC applied to resistor, AC applied to inductor. Now it's time to see AC applied to the capacitor. So just see the third part, AC to capacitor. So we have capacitor, suppose that we have learned in the electrostatic chapter, and AC is applied to capacitor, what will occur that we have to see. So we'll draw the diagram first. Suppose this is nothing but a capacitor, and to this capacitor we have applied this AC. Capacitor has capacitance C, capacitor has a capacitance C, and this AC voltage applied is E equal to E0 sine of omega t. This much amount of AC is applied to capacitor. Again here EMF is given, means what? We have to find the current and just see whether EMF and current are in same phase or how they are changing, that we have to find out. Accordingly we have to draw the waveform and phasor diagram, and some constant resistance we have to find out for capacitor. So before going into detail, we know the voltage is, suppose V applied across capacitor, voltage V is applied across capacitor and it has a charge Q, then we can say V equal to Q by C. That is the formula. V equal to voltage across capacitor is equal to charge on capacitor divided by capacity of capacitor or capacitance of capacitor. From this just we can find out, value of charge Q. Q equal to C into V. Move this C to this side. Q equal to C into V, capacitance into voltage. Okay, that is charge. Now what is the current? Current is represented by I. I is what? Rate of flow of charge per unit time. Suppose dq charge is moving, so I equal to dq by dt. dq charge per unit time dt, their ratio gives the current. Now here put the value of Q, so we can write here d dt of, what is the Q value? It is CV, C into V. But in our case, what is the voltage here? It is a EMF E. Instead of V, we represent it by E. So we can write this as a E here. And this we can write E here. So we get here E. So voltage in our case, we are representing that voltage by E. So we can write this as a C into E. Now what is the value of E? Put this value here and rewrite this. We can write d dt of C into E0 sine of omega t. d dt of C into E0 sine omega t. We have put the value of E. While just taking a derivative of this, C into E0, they are not function of time, take them outside. So this C into 0 C into E0 that we have taken outside. What is the derivative of sine omega t? Sine omega t derivative is cos omega t. So we can write here cos of omega t. Again derivative of omega t is omega. So we have just solved this part and just we have written I equal to CE0 derivative d dt of sine omega t is cos omega t into omega. So that we have written here. So we get this equation. So we can write this as, another way we can write this as, this omega first we can take omega into C into E0 cos of omega t. Same thing can be written as E0 divided by 1 by omega c. So this goes to numerator, E0 divided by 1 by omega c. Cos omega t is what? Sin omega t plus pi by 2. Sin omega t plus pi by 2, that is trigonometric formula, sin omega t plus pi by 2 that we can write. So just we will write this as into sine of omega t plus pi by 2. That is formula for cos omega t equal to sin omega t plus pi by 2 I equal. If we put this as I0, we can write I equal to I0 sine of omega t plus pi by 2. Just this is the final equation for current. If we see, if you remember, initially we have written same equation, but here instead of plus, here it is minus. So here the plus sign comes and this will give the current and this will give the EMF. Now compare these two equations. Then we can say current leads the EMF by pi by 2. Plus pi by 2 here it is. Now it will lead. If it is minus, it will lag behind. So it will lead the EMF by pi by 2. Another way, EMF lag behind the current by pi by 2. Same thing, just we have derived for a inductor also. Instead of plus sign, minus sign came there. Here it is a plus sign. So we can say from this total derivation of current from this equation, it is saying that EMF and current are not in phase. Current leads the EMF by pi by 2 when AC is applied to capacitor. Now if we see this part, just we have to draw the waveform that we have drawn earlier. So just we are going to draw the waveform. So I will draw it like this. Suppose such type of things that we have, that omega t along x-axis. Then we want to draw the waveform. As if we start EMF from 0 like this initial part, this is E equal to E0 sine of omega t. E equal to E0 sine of omega t. It will start at 0, but current leads the EMF by pi by 2. So current, instead of starting here, it will start somewhere here. Current will start in positive direction. So it will start somewhere here by 90 degree, and we can write this dotted line represent the current I equal to I0 sine of omega t plus pi by 2. From this what we can say? See, EMF is here, current is here. Current leads the EMF by pi by 2. So that is nothing but a waveform we have drawn. And for this peak of current, it is I0. For this peak of EMF, it is E0. Peak value of current and EMF. So these are the waveform we have drawn. Similar way, we can draw the phasor diagram also. So let's draw the phasor diagram as that given in your book also. So go to the phasor diagram. So we are going to draw the phasor diagram. So such type of thing they have drawn. So this again the omega t. Okay, omega t is taken along x-axis. Then what will occur actually in phasor diagram? What will they have shown? They have shown this as E0. E0 is a peak value of EMF. They have the angle. This is not omega. Omega t is the angle. So if we draw the perpendicular, this value is E equal to E0 sine of omega t. Here it is 0. Here it is a EMF. And what will occur with current? Current leads. It goes to more than EMF. So it will go to second quadrant, and that was represented by I0. If we draw the perpendicular, this perpendicular distance is what? I equal to I0 sine of omega t plus pi by 2. So this distance is that. So this is nothing but a thing, an angle between EMF and E0 and I0, that is peak value of current and EMF, is 90 degree here also. So that is a part that is said to be Phasor diagram for purely capacitor circuit. Now let's go further. As we have just put in this equation I0 as E0 by omega C, that I will write earlier first here. I will write here as I0 equal to E0 divided by 1 divided by omega C. Just we have written here 1 divided by omega C is nothing but like this we have put the value. If we compare this with Ohm's law, V equal to IR, I equal to V by R. So this is V, R. So this must be equal to resistance of capacitor circuit, and that is said to be capacitive reactance. In case of inductor, inductive reactance. In case of capacitor, capacitive reactance represented by Xc, and it is equal to 1 divided by omega C. What is the value of omega? 2 pi f. So we can write 1 divided by 2 pi f into C. So this is said to be capacitive reactance. Again, for AC and DC, you are going to find out what are the changes with the frequency and without frequency. So first of all, for DC, f is 0. If frequency is 0, 0 into anything it is 0, 1 by 0, Xc is infinity. Xc is infinity means what? It never passed the DC. It means what? Capacitor never pass the DC. Capacitor always block the DC. Why block? Because frequency for DC is 0. If you put it here, 1 by 0 is infinity. So capacitor block the DC. Inductor pass the DC. Second thing, for AC. AC has a frequency. So what is Xc? 1 divided by 2 pi Fc. So frequency is more, Xc is less. If the frequency of AC passing is very high frequency, it will oppose less. If the frequency is near to 0, it is less, then Xc will be maximum. It will not pass a low frequency signal, it will pass only high frequency signal. That is nothing but this thing that is said to be AC to capacitor. Capacitive reactance we have seen, inductive reactance we have seen. Okay, so these are the point we have seen when we apply AC to capacitor and AC to inductor. Next point of your syllabus is what? Just there is one table 13.1 in your book. In that table, what they have done, they have given a difference between resistance and reactance. Up till now we are well known about resistance, but after learning inductor and capacitor, the new word comes that is said to be reactance. Inductive reactance for inductor, capacitive reactance for capacitor. So what exactly difference between reactance and resistance that they have given? So just I will read it once. The resistance equally effective for AC and DC. Whenever AC pass to resistor, resistance is same for AC as well as it is same for DC. But what about reactance? Reactance is not same for AC and DC. Why it's so? Because it depends on frequency. So that for DC the frequency is 0, so reactance would be different. And when for AC it has a frequency, non-zero frequency, so its reactance is 0. In short, resistance is the same for AC and DC. Reactance is not same for AC and DC. They are changing with the frequency. So second, its value is independent of frequency of AC. That already we have learned. Resistance does not depend on frequency. While capacitive reactance inversely proportional to frequency, inductive reactance directly proportional to frequency. So reactance depend on frequency, resistance does not depend on frequency. Third, current opposed by resistor is in phase with voltage. Just we have drawn the AC applied to resistor. EMF and current are in same phase. They are not out of phase, they are changing similar to each other. But in case of capacitor and inductor, we have seen in case of inductor, current lag behind the EMF by pi by 2. In case of capacitor, current leads the EMF. So they are not in phase, they are changing continuously. Now the next topic is nothing but what? AC circuit containing resistors, inductor and capacitor. That we will see in next period. So just watch my video and try to understand and read the same topic from the book. Then you will again watch the video. It will increase your understanding. Let's see you in the next lecture. Thank you.